When we talked about atomic theory, we said that most chemistry takes place in the electrons, in the electron cloud of atoms. So it makes sense that there is a very important class of reactions called reduction-oxidation reactions, where essentially what we're doing is following the bouncing electrons as a reaction takes place. Recognizing different reaction types is a very helpful skill. It helps us classify things together and think about things in a consistent way. So that's what we're looking at now. We're looking at a specific reaction type of reduction-oxidation reactions. And again, just another reminder note, the word reaction is often abbreviated as RXN. So if you see RXN, think reaction. So what is a reduction-oxidation reaction? Well, as I just said, chemical reactions take place largely in the electrons. Now, depending what those electrons are doing, sometimes they're being shared, but sometimes they're being transferred. And when electrons are transferred during a chemical reaction, the result is a reduction-oxidation reaction, or we often shorten that to redox. So a redox reaction. So what are reduction and oxidation? Well, reduction is the process of gaining electrons. So we're transferring electrons. That means something has to lose and something has to gain. So reduction is gaining electrons. Oxidation is losing electrons. So when we've got a redox reaction, it's not an accident that we mash that together into one word, because these processes are coupled. We can't have oxidation without reduction, and we can't have reduction without oxidation. They both have to take place in a chemical reaction in order to balance out the number of subatomic particles that we've got floating around. So just like when we were talking specifically about ionic compounds, we said we can't just have magic loose electrons floating around and showing up and disappearing at will. We had to have them balance, and that's really why oxidation and reduction are coupled processes, because those have to balance. So when we think about that process, and this is kind of a twist around when we start thinking about terminology. The chemical species that is undergoing reduction, so reduction is gaining electrons, so the chemical species that undergoes reduction is causing oxidation to occur somewhere else. So by being reduced, it's causing oxidation. And because of that, we often refer to that chemical species as the oxidizing agent or the oxidant, because it's being reduced, which is causing oxidation to happen somewhere else. Going the other direction, the chemical species that's undergoing oxidation is causing reduction to occur somewhere else. It's a coupled process. So that species, the species that's being oxidized, is often called the reducing agent or the reductant, because, again, coupled processes, both happening together. How do we know that a reaction is a redox reaction? Well, one of the easiest things to spot is a neutral uncombined element as either a reactant or a product. Now, I've got to be careful here, because you can have redox without having any neutral uncombined elements. But if you see a neutral uncombined element as either a reactant or a product in a reaction, you can pretty much bet that it's going to be a redox type reaction. So just looking at a few chemical reactions here, here's our combustion reaction of hydrogen, right? This is also a combination reaction, because two substances are combining to form one substance, and it's a redox reaction because I have neutral uncombined elements, hydrogen and oxygen, forming water molecules. Similarly, we saw this one in combustion as well. What do we have? We've got oxygen showing up as one of the reactants, and it's combined in the product side, so this is a redox reaction. Magnesium oxide, another one that we already looked at. Magnesium, neutral uncombined element, oxygen, neutral uncombined element, forming magnesium oxide. And another one that we haven't specifically seen before is zinc, a neutral uncombined element, reacting with HCl, hydrochloric acid, to form hydrogen gas. So now we're reacting a neutral uncombined element and we're forming a neutral uncombined element. So that's a redox process. Specifically this last one, there are a few types of sort of sub-reactions within redox. This last type is also called single replacement or single displacement reaction. So a neutral uncombined element reacts with some ionic compound, usually an acid, to form a neutral uncombined element and a different ionic compound. So single displacement or single replacement are a specific type of redox reaction. One of the really nice things about redox reactions is that we can actually separate the two processes. In many cases, we can actually physically separate the two processes that are going on. And if we connect those with a wire, we just made a battery. Because what do batteries do? Batteries supply electricity. Electricity is just moving electrons. And when we're talking about a redox reaction, we're talking about transferring electrons between the reduction and the oxidation process that are taking place. So we can often physically separate these reactions, these half reactions. But even if we can't physically separate them into a battery, we can always separate them on paper. So here's that single displacement, zinc and HCl forming hydrogen and zinc. The reduction that's going on here is I've got two H pluses, right? So this is H plus reacting with two electrons, right? This is reduction. We're gaining electrons to form hydrogen, neutral uncombined element. The oxidation here is zinc, neutral uncombined element, reacting to form zinc plus 2 ions and liberating 2 electrons. So when I separate these, I can use those separate half reactions to balance the whole reaction, because all of the electrons that are being used in the reduction have to come from the oxidation, and vice versa. All of the electrons being liberated in the oxidation have to be used up in the reduction in order to have a balanced chemical equation. There are a couple of quick little mnemonics that are sometimes helpful when we're talking about redox, and these both get you to the same thing. They're just two different versions of the mnemonic. So if we think about oxidation is losing electrons and reduction is gaining electrons, we can remember that with the mnemonic oil rig, right? Oxidation is losing electrons, reduction is gaining electrons. If you're not into petroleum, we can switch that around and we can just rearrange the words. Losing electrons is oxidation, gaining electrons is reduction. So if you go to the zoo, you might see Leo the lion and he might say grr, right? So Leo, losing electrons is oxidation. The lion says grr, gaining electrons is reduction. Now again, we can classify reactions as multiple things. Sometimes they're always together, right? All combustion reactions are redox reactions, right? It's the nature of combustion. It's a redox reaction. In addition, many combination reactions, combination and decomposition reactions, are also redox reactions. That one isn't an all. So there are combination and decomposition reactions that aren't necessarily redox. But we'll find that a lot of them end up being redox as well as combination and decomposition when we classify them. So redox is a big field. Redox could be 2 or 3 chapters all by itself. We're not going to go into that much depth on redox, but it's a really good type of reaction to recognize because it helps us think about how the electrons transferring around are involved in chemical reactivity. Take a look at some redox reactions, and I will see you next time.